Good morning, everyone. In this class, I will make a quick revision on chapter 4. In this chapter, we have three main topics: mass equation, Bernoulli, and energy equations. Right. Please note that this chapter have been done via a Microsoft Teams meeting. We did about 3 classes, and these classes already recorded, so I'm gonna be a bit quick. This class is just like a revision. If you need more details, you're gonna back to the links that we record. Then you can see the full classes at Microsoft Meetings group. So we have three main sections in this chapter. Conservation of mass. I'll give you in just general introduction, very simple, something you studied in physics. Then we will have something about mechanical energy and efficiency, right? Then we will speak about the Bernoulli equation in details. We will have some examples. We need to know what is the hydraulic grade line at GL, energy grade line AGL, etc. Then we will have a quick look at general energy equation. Okay. So I need you to know there is something called conservation laws, which is applicable for anything, for mass, for energy, for momentum, especially when we have control or closed system, right? Please, I need you to go back to chapter 1 to read something, to make like a quick revision about the kind of systems and control volumes, right? Okay. So in general, when we speak about conservation of mass, it means that any mass, the conservation of any mass in mass dot n minus mass dot n is gonna equal delta mass for control volume over delta time. So this is the concept, and it's very basic and very logic concept. This actually applicable in fluid mechanics under something we call it continuity equation, meaning that if we have a flow in a pipe, this flow gonna be same unless we have a new mass in or mass out, right? That's fine. So this is the concept. There is some physical meanings about this concept. As example, the linear momentum in Newton's second law, conservation of momentum principles, linear momentum equation, all this you need to be able to differentiate them. This concept applicable also for energy. So energy dot n minus energy dot out is gonna equal difference or d energy over control volume over time, for control volume over time. So we must know this concept. So E dot n and E dot out is like the total rates of energy transfer, can be in, to, or out of the control system, right? So when we don't include time, it's like when we have anything over time, it's described the rate of a change, But if we don't include time, it's described the amount of a change, not the rate. It's similar to the distance and velocity. So distance itself, let's say when you say that I walk for 1 kilometer, so this is a pure distant meter. If you need to know your rate, your velocity, we must include the time. So you're gonna say, oh, I walk 1 kilometer in like 10 minutes, meaning that your velocity is gonna be 1 kilometer, which is equal 1000 meter over 10 minutes or 600 seconds, etc. So you're gonna use the unit that. So we need to understand the difference between the amount and the rates. So whenever you see over the t, meaning that there is a rate. If you don't see dot, so like E without dot, so this is amount. If you have dot, meaning that we have, it's a rate. It's a rate. I need you to understand this concept. Very important. Then we speak about conservation of mass. As you see, if we have 2 kg from hydrogen and 16 kg from oxygen, for sure, we're gonna have 18 kg from water. That's it. You need to know that we can convert energy to the mass. We have using this factor C, which is the speed of the light or light in a vacuum, which is equal 2.9979 times 100 million meter over second. Right? You need to know all these issues. Now, as I told you guys, we have mass, we have mass flow rate, we have volume flow rates. We need to understand the difference between this and that. In simple words, when you have anything over time, it's meaning rate. So if I have like if volume flow rate, the unit is gonna be meter cube over second. You see, this is the unit. Mass flow rate is gonna equal kg over second. You see, so mass itself, mass without dot, the unit is kg, but with dot, kg over second. That's also for the volume. If volume itself, meter cube. Volume flow rate, meter cube per second. Okay. If you remember, when we have a flow inside pipe, just like a quick revision for you, we don't calculate the flow rate or the velocity based on the maximum velocity in the middle here or in the minimum velocity by the wall side, by the pipe side here, which is approach zero. No, we have V average, then we calculate the velocity. We can do the flow rate. I need you to go back to chapter 2 to understand the concept of flow and remind yourself with the flow. We did some examples in chapter 2, right? Chapter 1 and chapter 2. Look at this figure, interesting figure. So we have mass in, mass out, delta mass for control volume. So this is value of mass kg, rates kg over second. Very simple, right? Another example here for mass balance. We spoke a lot about this when we have mass in, mass 1. We can have like many multiples in and multiples out. So as example, if we have mass dot in 2 kg per second, mass dot 2 3 kg per second, we're gonna have mass out 5 kg per second here, right? So it could be single stream, multi streams, etc. Right? You need to know all these issues. Yeah. So when we have two cases here, guys. When we have uncompressible liquid fluids like water or compressible fluids like gas. It's very simple in liquids because volume is constant, so no problem. Mass is gonna equal. We can control volumetric rate and mass flow rate, same. But when you have gas, look at this figure as example. Uh, if you have air compressor, this air compressor gonna compress the air, so the volume gonna be less, the output volume gonna be less. That's logic. So if you have mass in here 2 kg, then original volume was 1.4 meter cube per second. After air compressor, the output gonna be 0.8 meter cube per second. The volumetric flow rate is changing, right? But look at the mass, same, because mass can't be changed. kg, 1 kg, 1 kg, 2 kg, 2 kg, that's fine. But volume in only incompressible liquids like gases, etc. Right? We need to understand this concept. We did this example about volumetric flow rate. You see, I need you to read this example. It's very simple, very straightforward. Let me see here. Yes. Also, let me tell you something. We have what is the mechanical energy and efficiency. You see, guys, mechanical energy include three kinds of energy. I need you to understand this. One, flow energy, kinetic energy, potential energy. One, two, three. These three kinds of energy all together called mechanical energy, E mechanical. Each one have its value. So flow energy equal P over rho. Kinetic energy equal V square over 2. Potential energy equal G times Z, which is related to the elevation between the system and like datum or main sea level or any level. So it's flexible. So if you want to study the mechanical energy change, like changing grades, etc., it's simple. Now in this situation, you must have like case 1 and case 2, case 1 and case 2, P1 and P2, etc., V1 and V2, Z1 and Z2. That's how you can understand the changing in the mechanical energy concept. So you see, you must know that we between any two locations like 1 and 2 we have something called losses or irreversible losses. We're gonna speak about we have minor losses, we have major losses, we're gonna speak about we have friction losses. We did this in chapter 5 actually, if you remember. So we managed to calculate many kinds of losses, right? But you need to know if we have same pressure, density, velocity, and elevation remaining constant, then the mechanical energy won't change, it will be constant. You need to understand this, right? Very important. Now, if we assume that we have typical condition that don't provide us with any losses, meaning that the mechanical energy change represents the mechanical energy supply to the fluid, meaning that if I have like a frictionless pipe where there is no losses at all, there is no valves, there is no T sections, whatever, so and there is no friction. So if the water in such imaginary pipe, which is not existence actually, will flow for like 10,000 kilometers without stopping. But that's not logic. So, but if we assume that we have this case, so the mechanical energy will be constant unless we supply it, meaning that we add pump, we like install pump that will feed the system with mechanical energy, or if we like extracted this energy via like a turbine, etc. So in the first case, delta E mechanical will be more than zero, bigger than zero, and the other case when we install turbine to abstract or to extract the liquid the energy, then meaning that the total energy, the difference in the mechanical will be less than zero, right? Look at this figure here. So just a little talk about turbine. Turbine concept, just a quick remind. I need to remind you about turbine concept. That it's convert the mechanical energy that included in the flow to electrical energy via a generator. So we are using the shaft energy that is produced by the movement of the water, right? This is shaft movement. We convert it to the electricity using generator, and we have some details here, right? Now let's speak about Bernoulli equation. Bernoulli equation is an approximate relation between pressure, velocity, and elevation, and it's valid in a region of steady, incompressible flow where the net friction force are negligible. So again, you remember these three components: 1, 2, 3, flow energy, kinetic energy, potential energy. Now we have equation that control the relationship between them, called Bernoulli equation. But this Bernoulli equation is valid in a region of steady flow, meaning that if we have unsteady flow, we can't apply Bernoulli equation. Incompressible flow, so it's applicable only for liquid. So we can't apply Bernoulli equation for gases, right? And where there is no frictional forces. So when we have any frictions, meaning that Bernoulli equation is not valid. So that's why we have Bernoulli equation, we have other equations. That's why we have other equation like general energy equation, etc. We have many equations. So this is the limitation of Bernoulli equation. You can see here, when we have steady flow, we will be able to use Bernoulli equation. But in this zone, we can't use Bernoulli equation. Derivation, it's not required from you guys. So this is the summary here for the equation, meaning that these three terms of energies, these three kinds of energy will be same. The concept, the simple concept of Bernoulli equation, that pressure energy, kinetic energy, potential energy are constant along the stream time if we don't have friction and steady and etc. All these three conditions. And this is the form of the equation. These conditions must be applicable before we use the equation. So in simple words, this is the equation. We can write it in different ways, like we can use like P over rho G. We can divide all these terms by G, then we can get Z alone here, distance, which is like called head. So we have three figures to describe the Bernoulli equation, right? We need to be able to understand this three. So this one, two, and this one here, right? But the concept is same. Sometimes we need to use this concept by pressure. So we must keep pressure alone. So we times all by density, because density is constant, so it's fine. So we keep P alone. But if I have more information in in distance, in the heads, which is present the energy, but in units of in distance unit, meter. So we're gonna use it here. So we have this form, and we can have pressure only form. So it's interesting, right? So you need to understand this equation. More details about Bernoulli equation here. So when we don't have steady or compressible flow, we can use integration to do this equation, but we must include friction at losses, HL losses. We must include any pump if we have, or any turbine if we have. We're gonna speak about this case in next section in general energy equation, right? So this is also the general energy Bernoulli equation in terms of pressure. You need to understand this also. We did this again. Okay, guys. In some cases, we have something called stagnation pressure when we have water flow. So in a pipe, if you insert the pipe at the middle of the, if you insert another pipe, thin pipe, or tight tube, sorry, in the middle of the pipe, there is extra length here, there's extra pressure energy, which is equal V square over 2G. You see here. I'm gonna give you more details. So we can do the equation here using that this is equal V square, velocity here at the middle, over 2G. If you don't add, this is only represent the pressure only here, static pressure, right? Some details about stagnation stress streamline. Here there is a limitation. The limitation on use of the Bernoulli equation, like steady flow, frictionless flow, must be no shaft work, incompressible flow, no heat transfer, flow through a long streamline is not applicable for Bernoulli equation. You need to understand this as well. This figure represents some of the cases that limit the use of Bernoulli equation. Now, guys, we have two concepts of hydraulic grade line, HGL, and EGL, energy grade line. You see, guys, these two terms, first of all, are imaginary values to represent the total energy included through any flow line or water pipes, etc. The first term, energy grade line, include the three terms here, 1, 2, 3. The hydraulic grade line include only two terms, P, the first one, and the last one. The velocity here, term, the kinetic pressure here is not included in HGL. So the energy grade line EGL include head pressure, velocity head, elevation head. Hydraulic grade line include pressure head and elevation head, not included in the hydraulic. The velocity head is not included in HGL. Why we need to know this? Look at this figure. It will help you. You see, guys, the dotted line here is represent EGL, HGL, and the solid line represent EGL. You need to know that EGL is always equal or more than HGL. That's you must know. Number one. Number two, when we have velocity zero, when we have no velocity zero, EGL will equal HGL because this term gonna be zero, the dynamic head, right? Okay. So when we have velocity zero, so the value will be zero. The HGL will equal EGL here at this point, right? Very simple, very logical. Now, so when we have small pipes, so as I told you, we have continuity flow. The flow here is gonna be same in the small radius pipe and the bigger radius pipe. So in this side, right, we will have high velocity. Here we will have a small velocity because the flow is gonna equal V times area. Area here is big, but area here is small. So velocity is gonna be bigger here and velocity is gonna be small here. That's number one, you need to understand. So if we install two pipes here, one at the toe at the edge and one in the center. So the one in the center will be affected. Will the height, the dynamic head will be included here. You see the level here will show the level, but the one at the edge won't show the velocity because velocity almost zero at the edge here, right, at the pipe side. So this pipe will represent total energy or EGL, energy grade line, but this one will produce hydraulic grade line without velocity, and you'll see the difference. So here the difference in the small radius pipe is bigger than the difference in the big radius pipe because the velocity is smaller here. But in general, you see there is a drop. There is a drop, meaning that we have losses here. That's why the total energy is uh, uh, dropping or declining with the distance because we have friction losses. We have another losses. So look at this figure. There's some details here about HGL and EGL. But look at this figure here. If we have bump, how we can increase the total energy by installing bump? Look, both line will be increasing EGL and HGL. But if we have turbine, both will be dropping, right? That's very logic. You need to understand this. Okay. Okay, now I need to give you some examples about some applications on Bernoulli equation. Actually, we did this many times, but I will repeat it for you. So if this is very common example, look here when we have water tank and when we have outlet here. So we have two cases, case number one and case number two, right? So pressure, this is open to the atmosphere. So atmospheric pressure here is gonna equal atmospheric pressure at the exit here. So B1 with B2 gun with gun. I told you for any lake, any like water body that the exit is just like a small pipe, we can't notice the velocity here, the changing in the velocity. So we're gonna assume velocity is zero, almost equal zero, but we're gonna keep V2 because you can see the water is flowing, moving. So we have velocity. So V1 equals 0, but we keep Z1, which is, so we assume our datum here, just Z2 is gonna, then Z2 is 0. So at the end of the day, we will have this equation for. But this is only for this case if we have this open to the atmospheric pressure. But if it's closed as example, so we can't remove B1. We must know how much pressure here. I will show you example later on about this case. So you must be careful. This is applicable for when we have uh, open tank, etc. Right. We have another nice case here when we have like a boy playing with water. Right. So like spraying. So we will have this case. We have, look here, we have one at his finger here. We have one and we have two here. Okay. So what we gonna do, guys? Look, so we will write the equation for case number one, case number two, but we must be careful about everything. So at number one, we can expect that this water will be rising for like 20, 30 meter, whatever. So you see, we can't like assume that the pressure is same. So there is a little bit difference in the pressure. But what we're gonna do, we will know that you look at this figure here, so we will know that the velocity here, we can assume that there is big difference between V in the outlet and V in the inside the hose here. So we're gonna assume V1 is 0, Z1 is 0. I take my datum here, so I keep P1, I keep P2, which is atmospheric pressure here, and then V2, the water will stop when there is no velocity. Water will keep rising up, rising up, rising up till there is no velocity, then stop. So V2 gonna be 0. So we have this equation, then we can solve this equation. This is just like, you say, imaginary case. This is real case. This is just like more imaginary case, right? So we have two examples here about these two cases. Please read them again. Also, we have example 5 number 5.8 in the textbook. You can read this. This is very simple also about pipette tube. So just direct application of the equation. I will, guys, this example is already done. And today I will make another class also to solve another 6 examples for you. So I won't invest too much time in these examples because it's very simple and very straightforward, right? Okay, guys. Yes, this is very simple, straightforward, just direct application of the Bernoulli equation. The main concept that, as you see here, you need to know that we have, let me just give you some, how how we can. So we have two cases, guys. We have 1 and 2. Z, the both is same level, so Z1 gone with Z2. Why the critical question here? Why we assume V2 is 0? You see why, guys? Because in this tube, water must be stable. There is no velocity at all, because if there is velocity, water will rise up and keep flowing. As long as we reach the stable condition here with this level, meaning that there is no velocity. Finish. So I can say V2 is equal 0. So that's how we can keep the equation that way. Right. Now, what is B1 and what is B2? Remember rho GH. Rho GH here, this is H1, this is H2. There is no H3 this side, right? B2 is we have the three levels. H1, it's about 3 centimeter, H2, 7 centimeter, H3, 12 centimeter. So that's how we can use B1 and B2. So after that, you can just carry on with the example, with the numbers. Same concept. Then you can calculate V1. But this is very important example. I need you to understand it very well. Right. Let's have a look at general energy equation. I don't need you to lose your, I mean to miss you, sorry. There's too much details about energy and efficiency and all these issues. I need you to understand the main concepts. Then we need to know how we can apply this this equation in our hydraulic application. The simple words here, the general energy equation is quite general equation that applicable for all systems, even when we have friction, unsteady, steady, non-steady, we have pump, we have turbine, we have head losses, we have everything. So here is we can use this equation. Let me just show you the outcome from all these things. I need you to look at this equation. It's Bernoulli equation, same typical, just we add pump at the left side. If we have head pump, we add head turbine at the right side, and we have head losses. So let's say that we don't have pump, so 0. Let's say we don't have turbine, 0, finish. Let's say we don't have HL, it's going to be 0, so we go back to the Bernoulli equation. But in general, we must have at least one of these three values, pump or turbine or HL, or three of them. You need to understand the system. Now let me go back, show you something. We have some concepts, guys, I need you to read them, like thermal energy, heat transfer, uh, adiabatic process, heat transfer. Let's just have a look here, get some knowledge. You see, guys, as example, look at this figure here. When we have mass at the top of the mountain, so in this case we have potential energy for it, 10 kilojoule, but kinetic energy 0. There is no velocity, so 0. If we drop it, so potential energy will lose 3 kilojoule, but this 3 kilojoule are converted to kinetic energy. This is how we can understand the concept of energy. conservation. There is no losses. There is nothing lost in the energy. Energy convert from shape to another shape, from potential to kinetic to pressure to flow to whatever. Even we can convert by Einstein regulation, we can convert the mass to energy by using the C factor, light of so speed of flight at the vacuum. So I don't want to go in deep in these issues, but we need to understand this concept, right? This is like called the first law of thermodynamic conservation of energy. Energy can't be created or destroyed during a process. It can only change forms. This is very typical. This is very important concept. So again, energy can't be created from nothing or destroyed or like disappeared. No, it can only change forms. You understand? So whenever we have energy, it will be there, but in different forms. That's fine. You see the same concept when we have energy in minus energy out, delta E is gonna equal delta E. So if you need to include the time, we're gonna over time, so we're gonna use E dot, that's fine. Now we have some like more details about how we can present the energy. So you see, we can use like term Q dot, which is more like the work. You see the rate of energy, it's called work. It's called like work. So we're gonna use work, and there is like a rate of the work. So there's some details here in the energy things. Yeah. So you will need to have like a quick overview about it. So there's some like more like unnecessary details for us as a civil engineer, but you need to know it actually. For example, if I have system here, so I have a Q in 15 kilojoule, right? I have a Q out as like 3 kilojoule, but also I have another shaft energy in shaft, like rotational movement by kilojoule. So the delta E over all this system, we have 15 in here, we have minus 13, and we have plus 16. So the delta E over this system is gonna be 18 kilojoule. You understand? So that's how we can understand the situation. So Q net in gonna equal Q dot in minus Q dot out. Same concept. Work net in gonna equal work dot in minus work dot out, etc. All these details must be like understood. So as example, as I told you, how we can transfer the energy by work. So what is work? It's like the energy transfer associated with force acting through distance. So in general, work equal force time distance. So related to the energy transfer. We have some concept of power, which is like the time rate of doing work. The time rate of doing work. Okay, so we have different kind of work. We have shaft work, we have pressure, we have viscous work, we have many others. So this is the definitions about this work, right? So don't confuse yourself between like energy, work, power, all this. Just take it simple. Just read the definition, understand them, finish. What is shaft work? Shaft work is very important for us as civil engineer because it's produce the movement. It can produce the movement, right? So it's connected. It's like engine, any engine. What the engine work? Engine receive like electrical energy and convert it to the rotational work by rotational, which is called it produce torque, which is like a momentum F times R here. So this torque will move the boat, as example, will move the car, will move everything. So that's why it's important. So shaft work is a force of acting if you imagine like a force F acting through a momentum arm, the radius is r, so we'll generate like a torque equal T that way. This is the equation, right? So here we have like the force act. What is the distance that the first force acting? It's the diameter. The diameter, right? So times how many rotations? So we're gonna use this equation. So shaft work will equal this force itself time distance, which is equal this equation. So this is kilojoule. Then we have shaft itself. This is epsilon here is like a factor to convert work shaft to the energy, right, etc. There is like a derivation of the equation here. There is take it simple like that. You see, when we have minus it, we have some in here, out here, right? So we will have like, and when we have fixed control system, guys, we will be able to analyze the system. It's depend on the three mechanical energy, but you see, we times by m to get the work because we can't here deal just with that because the concept is related to the amount of actually work done, which is then we must have mass inside the equations. That's why we can't avoid adding mass here because we are dealing with um, uh, we don't deal only with like flow rates. No, we need to know how is the amount of mass that included in the system. So that's why we include mass here. Okay, so guys, yeah, so when we have this mechanical energy, when we times with mass, we will have the work and the energy needed for the system. So this is just like derivation. I didn't so this is the summary here. This is the conclusion. I need you to understand this. It's just very typical, very similar to the Bernoulli equation, but we added turbine here, and we add pump here, turbine, and HL here. So you see, guys, here we have, okay, so you see there's some definition about everything. We have something about efficiency. I did all think actually. You need to know that the concept of efficiency. Let me just. This figure will help us about the efficiency. Let me tell you something about efficiency, guys. When we have pump, when this pump like consume 30 kilowatt from electricity, it won't convert this 30 kilowatt as like a pure work. No, there is like efficiency. Let's say if the efficiency is 70%, so we're gonna lose 30% as like a loss. It's not losses in terms of losses, but it will convert it to another kind of energy, right? So this is the efficiency. Also, if we reduce energy by turbine, like this turbine, let me just show you. If we have this turbine, where is that turbine? Here. So let's say this turbine consume like 30 kilowatt energy from the water here. It won't be produce 30 kilowatt electricity. No, there is efficiency and there is some losses. So we need to understand this concept of efficiency, right? This figure will help us to understand it. So as example, to understand the general energy equation. If I have mechanical energy here, these three terms, N. So let's say I have pump here, W dot pump. Some of the mechanical energy of the pump will be losses here outside, so it won't contribute total, so it will contribute a little bit, so some of it will be out. Let's say I have turbine here. This turbine will abstract this amount of energy from the flow, but the output here will be there is some losses. So we can't get benefits from the total energy that already abstracted from the flow, right? So at the end of the day, we will have also another HL here, another HL. It's like mechanical losses from these three terms for friction, for everything. If we have valve, if we have whatever T's, etc. So this figure very interesting, will help you to understand the general energy equation. So if in Bernoulli equation we was assuming that this term we have only this term and it will be same all the time. So like P1 over G rho G plus V1 square over 2G plus Z1. We was assuming this term to be same value when we have 2, 3, 4, but now no, we have losses. So we have pump like here, it will contribute, increase the energy. When we have turbine, it will abstract some of the energy. There is some losses for the turbine and for the pump. Then we have HL. So this figure will help you to understand the general energy equation. So if we don't have pump, that's fine. We keep like that. If we don't have turbine, that's fine. But for sure we will have HL. So you must understand this concept. General energy equation here again, different form, different figure. You will see that we know that Bernoulli equation is like a special case of general energy equation. You see guys, sometimes we have factor if we go for like actual situation, because the density, the flow profile for, especially when we have like unsteady flow, turbulent flow, unsteady flow, whatever, the velocity profile will affect the behavior of the equation. So that's why we add a new factor, which is called kinetic energy correction factor. Kinetic energy correction factor, which is necessary to adapt or to handle the different kind of velocity profile. So we can use it for special cases actually. When it's mentioned, mainly it's gonna equal 1. If it's not mentioned, so you're gonna take it as 1. This value will be between point 1, the value of the value, or the correction value, is gonna equal 2 when we have fully developed laminar pipe flow. So that's the factor. But it will be between 1.04 and 1.11 when we have fully developed turbulent flow. And you need to understand what we mean by fully developed. Go back to chapter 2 to understand what is the meaning of fully developed, etc. All this, sorry, chapter 5. We already discussed this concept, the fully developed flow, in chapter 5, the first slides, right? So this is the final form of the equation. We just added here the correction factor, kinetic energy correction factor. If it's not mentioned, then you're gonna use 1, finish. Right? Very important for you. We have 2 examples here, guys, about one example about turbine, other example about pump. I did these examples before. So in summary, in a few words, in this section in general energy equation, I need you to understand this equation, some concept about energy, power, work, etc. Then I need you to understand very well these 2 examples. If I ask you in the test or the final exam, my question will be very similar to these 2 examples, right? I won't make like difficult equation in general energy equation, but you should expect something like not easy in Bernoulli equation, right? General energy equation. Look at this figure. We have turbine. that produce energy, electrical energy via generator. So we have case 1 and case 2. The elevation difference 120 meters, which is quite enough value to produce energy. Right, so the volumetric flow rate is 100 meter cube per second. Head loss is HL35, and we have turbine. We need to know how much this generator can produce electricity if we know the efficiency is 80%. So let's understand the concept. We have one and two. The both side before the dam and after the dam, it's atmospheric pressure. So B1 gun, B2 gun. V1, you can see the water when it's going down. No, the flow is gonna be little. So I mean, in term, if you the flow in this pipe here won't make any like noticeable changes in the level here. Also here, so V1 and V2 gun. So what we have? We have Z1 here. Z2, we're gonna assume our level here to 0, so it's 2. So we we don't have any bump. You see any bump here? No, we have just turbine and we have HL. So the equation will be summarized to that way. You see, it's interesting. We have two equations also to convert to know how much work produced by turbine. So m dot mass flow rate times G times H turbine. So from this equation, we're gonna get H turbine, then we take it here to know how much energy produced. Then the electrical energy, the net electrical energy must be times by the efficiency turbine generator, which is 80 here, right? So go back here to the equation. You can apply, here. You can apply the numbers, so you can see H turbine is gonna equal Z to 1 minus 35, it's 85. You take this value times G times M mass. You must know how to get this value. Then we have 83 kilowatt. Then because efficiency is 80%, it's gonna be 66.7 megawatt. It's very simple, not difficult at all. We have different case now. It's more about pumping power from a lake. We need to know how much, what is the required there. This is gonna use same equation, but we don't have turbine here. We have pump and we have water here in the river. We need to shaft, or we need to pump it to the pool here. We have 25 level difference. So we after analysis everything, atmospheric pressure almost same, B1 gonna equal B2, done with done. Also velocity won't be included because V1 here and V2 is gonna same. So after that we will see that this is the equation. W pump will be equal mgz2 plus E mechanical energy. That's it. So we must understand before we go to the pump itself, we need to know that delta B here, the delta B inside the pipe, the pressure, because in the pressure here we will in the bottom we will have more pressure at the top here. So we're gonna do something related to the pump itself. For the pump, this is not for the system, this is for the pump. So pump B out is gonna be B out minus B in is gonna equal delta B, which is equal the PLU pump over the volume, right? W dot pump over the volume. Let's see how we can do the solution. So let me just remind myself with the example what we need exactly here. So actually we need to determine the discharge rate of the water and the pressure difference across the pump, right? So we have the pump shaft power of 5 kilowatt, efficiency 73. It's gonna pump water for 25 meter, right, from the lake to the top of the house as example. If we know that the head losses here is 4 meter, we need to calculate two things. The first one, the discharge rate, how much this pump can do discharge rate. Then we know how much time needed to fill the pool if we have the volume as example. And the pressure difference across the pump. So first of all, we know the pump capacity is 5 kilowatt. So the net energy that can be produced by pump is 5 kilowatt times 0.72, which is efficiency 30.6. The net. This is the net. We know now B1 equal B2, B atmosphere, V1 equal V2, almost zero, done as I told you. So we're gonna summarize this equation, gonna be that way. So just substitute numerical substitution. We will have V dot is gonna equal M dot over B, or that. So this is what we called um, volumetric flow rate. This pump can do 12.7 liter per second. Nice amount, by the way. See, in 1 second can pump about 13 liter. It's not bad, right? Okay, so then we need. I know we know the flow rate. Very simple. Using this value, we substitute in this equation. We're gonna know the difference in the pump, delta pump. It's gonna equal P out minus P in, which is equal about 283 kilopascal. By this slide, we almost finish chapter 4. I will record another class for the 6 examples. Then I will upload it for you. Thank you so much.